Usually when we talk about a computer making a mathematical error, we kind of just assume something has gone terribly, horribly wrong.
Right, like the classic blue screen of death.
Exactly. I mean, we expect absolute flawless precision down to the very last decimal point, right? That's what computers do.
Well, yeah, that is the entire foundation of traditional computing. It's binary, it's exact. A 1 is a 1, a 0 is a 0. And if a calculation is off by even a fraction, the whole system just crashes.
But what if I told you that making a computer deliberately worse at math is actually the secret to unlocking the future of artificial intelligence?
It sounds totally backwards, I know.
It really does. But welcome to the deep dive. Today, we have this fascinating mission for you. We are exploring a complete paradigm shift. It's called approximate computing, and it is completely revolutionizing edge AI.
It really is a complete inversion of how hardware engineers normally think about their jobs. They're basically unlearning decades of best practices.
And to guide you through this, we've got a really great stack of fresh research today. Instead of just, reading a textbook, we are pulling from a massive 2022 survey on hardware techniques by Arminiakos and his team.
Right. And we also have that really cutting edge paper by Garcia and colleagues, the one on training algorithms.
Yes, and to tie it all together, we've got this visual approximate AI blueprint filled with diagnostic matrices and performance graphs. Together, they point to an industry that has essentially hit a massive physical wall.
A literal physical wall. The data in these sources paints a very stark picture. I mean, we are literally running out of power.
And I'll tease this right now. So you stick around. By the end of this deep dive, you're going to understand how intentionally introducing mathematical errors might actually be the ultimate shield to protect AI from hackers.
That part is just mind-blowing.
It's so cool. Okay, let's unpack this. Why would we ever, in a million years, want a computer to make mistakes?
Well, to understand the why, we first have to look at the sheer scale of the energy crisis that's currently choking AI development. And it all really comes down to something called the multiplier bottleneck.
The multiplier bottleneck. Let me guess. We're just multiplying way too many things.
Put simply, yes. I mean, modern convolutional neural networks, the kind of AI that does like image recognition on your phone or object detection in a self-driving car, they require tens of billions of multiply accumulate operations.
Wait, tens of billions just to make one prediction.
Just for a single prediction, yeah.
Multiply accumulate. Just so we are all on the same page here, what does that actually look like under the hood?
So we call them AMSI operations. You take an input, like the color value of a specific pixel in an image, you multiply it by a weight.
Which is basically how important the AI thinks that pixel is, right?
Exactly. And then you add that result to a running total. So multiply, accumulate, over and over, billions of times. And the heavy lifting here is done by what are called general matrix multiply, or GEM.
GMM, got it.
Yeah. And according to the blueprint data we're looking at, these GMM operations consume over 70% of the total inference time for an AI model.
Over 70% of the time is just spent doing multiplication. That is, wow. There is a great visual in the blueprint that illustrates this perfectly.
The scale graphic.
Yeah, the scale. On one side, you have GMM, the multiplication, and it's drawn like this massive, heavy cinder block. And on the other side, you have simple addition, which just looks like these tiny little pebbles.
That visual is incredibly accurate, honestly, because that metaphorical weight translates directly into electrical weight.
Like actual power draw.
Exactly. Multiplication circuits require a lot of physical logic gates on a silicon chip. And when you try to run billions of these operations on edge devices, meaning, your smartphone, a smartwatch, or some tiny remote sensor.
Right, things that run on a battery.
Exactly. This massive requirement for exact high precision math creates extreme power density. If we tried to run full-scale exact AI math constantly on these tiny chips, we would literally risk melting the battery.
Wait, melt the battery? Come on, isn't that a bit of an exaggeration?
Yeah.
Because I know when my phone gets too hot, it just throttles the processor and everything gets super sluggish.
Right. But your phone throttles specifically because the thermal runaway would be catastrophic if it didn't. The chip has to forcefully slow itself down just to survive the heat generated by all those precise multiplications.
Oh, I see.
Yeah, so in a constrained edge device, you simply cannot run high-end AI without thermal throttling just completely killing your performance.
Okay, so it's almost like trying to commute to work every day in a Formula One race car. Sure, the F1 car is incredibly powerful and precise, but it's going to burn through a tank of gas instantly, and it's absolutely going to overheat just sitting in city traffic.
That is a perfect analogy. We don't need an F1 car for the edge.
We need a bicycle.
Yeah.
So the question becomes, how do we do complex AI math without actually doing the exact math?
And that is exactly the problem hardware architects faced. To solve your F1 car in traffic problem, they had to fully embrace approximate computing. By intentionally allowing these controlled mathematical errors at the hardware level, architects realized they could trade a negligible fraction of accuracy for massive nonlinear gains in energy efficiency and speed.
And the blueprint calls this the Atlas of Approximation, which sounds very epic. So what does this actually look like in practice? Where do we even start cutting corners?
Well, the first instinct was just to make the numbers themselves smaller. This is called precision scaling. We basically compress the data width.
Meaning what exactly? Are we just chopping off decimal points?
Essentially, yes. In traditional cloud computing, you might use 32-bit floating point numbers. They have this incredible precision, stretching far, far past the decimal point.
Right, highly accurate.
But precision scaling squashes that down to, say, 8-bit integers. It's like rounding a 20-digit number to the nearest whole number.
Oh, wow.
Yeah, and it takes way less memory and way less power to multiply two 8-bit numbers.
Okay, so shrinking the numbers helps. But what if the sheer volume of math is still just too high? Because I imagine, even if they are 8-bit numbers, billions of multiplications will still drain a smartwatch battery pretty fast. Can we just, I don't know, skip some of it?
We actually can. And that brings us to the second vector, computation reduction. It's all about predicting and bypassing redundant work entirely.
Bypassing the work.
Yeah. The Armeniakos survey outlines two very clever techniques for this, which are skipping and memoization.
Skipping sounds pretty self-explanatory, I guess.
It is, yeah. If the hardware detects that an AI is about to multiply a number by something very close to zero, it realizes, hey, the result is going to be basically zero anyway.
Right, anything times zero is zero.
Exactly. So it dynamically powers down the multiplier circuit for a fraction of a microsecond and just outputs a zero. It skips the math entirely.
That is incredibly practical. Just turn it off for a second. What about memorization? That sounds a lot like memorization.
It's very similar. So if the hardware realizes it just calculated a specific input pattern like a millisecond ago, it doesn't spin up the multiplier to do the math all over again.
Let me guess. It just remembers the answer.
Right. It just pulls the old answer from a tiny dedicated cache memory.
Okay, so if it knows 5 times 5 is 25 from a millisecond ago, it just writes down 25 instead of actively calculating it again.
Precisely.
But hold on, I have to play devil's advocate here for you, the listener, because we're talking about making the numbers less precise, skipping math entirely, just guessing that things are zero. If I'm using an AI for, say, a medical scan to detect a tumor, I really don't want close enough math. I want absolute perfection. Is this safe?
That is such an important question, and it's crucial to distinguish here between cloud AI and edge AI.
Okay, what's the difference in this context?
For critical tasks like a high-res medical scan, you run that on massive servers in the cloud where power draw really isn't an issue. Approximate computing is specifically for the edge, the battery-powered devices in your hands.
Right, the smartwatch or the phone.
Exactly. And what's fascinating here is that these techniques rely on the inherent error resilience of neural networks.
Meaning the AI can handle the mistakes. It doesn't just break.
Right, it doesn't break. Remember, a neural network is loosely inspired by a biological brain. And your brain doesn't need absolute mathematical perfection to recognize a cat.
That's true.
If it's dark outside, or if a tree branch is blocking part of the cat, your brain still says, yes, that's a cat. A neural network is the same way. If a few internal pixel calculations are skipped or slightly rounded off, the network's overall prediction doesn't shatter. The collective weight of the billions of other calculations just carries it through.
Okay, that makes a lot of sense.
Yeah.
The system is naturally squishy, so we could afford squishy math. But what about the math we absolutely have to do? You know, the operations we can't just skip around away.
Well, that leads us to the most radical approach in our sources. If multiplication is the cinder block weighing down the whole system, the ultimate hardware optimization is to just kill the multiplier entirely.
Wait, do multiplication without a multiplier? How is that even physically possible?
This is where we enter the multiplierless paradigm. We replace the big, heavy multiplier with simpler, approximate adder units.
Okay, I want to explore this because there was this specific example in the blueprint that took me a minute to wrap my head around. Let's slow down for a second because Doing math via audio is always kind of tricky.
It definitely is.
Say the AI needs to calculate 7 times x. Normally, you'd send that to the power-hungry multiplier, but here you translate it into what's called a multiple constant multiplication problem.
Exactly. Instead of a dedicated multiplication circuit, you use a bit shift and a subtraction. In the code, it looks like this x shifted to the left by 3 bits, minus x.
Right, and when I first read that, my eyes kind of glazed over.
Mhm.
But let me try to translate this for everyone. If we want to multiply a number by 10 in our normal, everyday base 10 number system, we don't really do math, right? We just add a 0 to the end. 5 becomes 50.
Precisely. You were just shifting the digits.
So in binary, which is the language of computers, shifting the bits to the left does the exact same thing, but it multiplies by powers of 2 instead of 10.
Right.
And the magic here, as I understand it, is that moving a number over by one slot in physical hardware costs basically 0 energy. It's just routing wires differently. So shifting x by 3 bits effectively multiplies it by 8, basically for free.
It costs 0 logic gates. It is functionally free.
So you get 8 times x for free, but wait, we need 7 times x, so you just take that free 8x and you subtract 1x.
And subtraction is really just a form of addition, which we know from our scale analogy is incredibly light and energy efficient.
So it's almost like paying for a $7 item by handing the cashier an $8 bill and getting a single dollar back. It's a massive shortcut compared to pulling out 7 individual $1 bills and counting them one by one.
That's a great way to visualize it. And if we connect this to the bigger picture, it doesn't just stop at one single calculation. The real power comes when you scale this up using something called an adder graph.
Because an AI model isn't just multiplying by 7 once, right? It's multiplying an input by thousands of different weights simultaneously.
Right. And instead of calculating each of those weights completely independently, an optimal adder graph shares the intermediate results.
How does that work?
Let's say the AI needs to multiply an input by 5, by 22, by 40, and by 58. Instead of 4 separate complex operations, a single shift and add sequence can be tapped at multiple points.
Tapped, like a maple tree.
Kind of. You calculate the 5x, and then you use that 5x result as a stepping stone. You shift it again to get 40x. You add to it to get 22x. It's this cascading web of shared logic.
Oh, I see. It's like carpooling for math. Everyone shares the same route, doing the exact same addition until they need to hop off at their specific exit for their specific weight. It massively reduces the total number of logic gates needed on the chip.
It's incredibly elegant, honestly.
But hold on. If shift and add architectures are so incredible and save all this energy, why isn't every single chip in my house built this way right now? Like, what's the catch?
Because there's a very significant catch. You can't just take a standard off-the-shelf AI model, drop it into a multiplierless chip, and expect it to work efficiently. There's a fundamental disconnect between the software and the hardware.
And this is where the Garcia paper comes in, right? Because they realized that if you just randomly compress an AI's weights, you might end up with numbers that are really expensive to build an adder graph for.
Exactly.
Sure, 7 times x is easy, pay with an 8, get 1 back.
Yeah.
But what if the AI randomly decides its absolute favorite weight is 113?
Right. To calculate 113 using only shifts and adds might require a messy, long, power-hungry chain of operations. The hardware efficiency is entirely at the mercy of the specific numbers the software happens to choose during its training phase.
So how did Garcia and his team solve this disconnect?
They developed something called hardware-aware training. They realized the software and the hardware have to be co-designed from the start. So they integrated the physical cost of the silicon directly into the software's training loop.
They created a metric called the SCM score, right? Single constant multiplication. It literally tells the software exactly how many physical adders it will cost to compute a specific number. But how does the AI actually use that score?
Well, during the training phase, an AI learns by doing cycles or epochs over the data. Every few epochs, the Garcia system steps in and evaluates the AI's weights using that SCM score. It then fixes or freezes a percentage of the network's weights.
Let me make sure I'm getting this. In their tests, they use networks like ResNet 18 and ResNet 20.
Right, those are standard, heavily used image recognition neural networks that everyone uses for benchmarking.
So they take the standard image network, and every few cycles, they freeze about 10 to 20% of its weights. But it doesn't just freeze random weights, does it?
No, not at all. It looks at the SCM scores, and specifically freezes the weights that are mathematically cheapest to implement in physical hardware.
Wow. So the AI is literally being forced to learn how to make its prediction
Yeah.
using only the numbers that are cheap for the chip to compute.
Yes.
If the AI wants to use a really complex, expensive number, the training algorithm basically gently pushes it toward a cheaper number nearby.
Exactly. The software is actively adapting its brain to fit the physical constraints of the body it will eventually live in.
And the results from the Garcia paper are just staggering. By using this progressive hardware-aware approach, they achieved a 25% global reduction in LUT usage on FPGAs. Now, real quick, for anyone not building custom silicon in their garage, what is an FPGA and an LUT?
Sure, an FPGA is a field programmable gate array. Think of it as a blank canvas of silicon. Instead of a chip being hardwired at a factory, engineers can reconfigure its physical logic gates on the fly.
Okay, and the LUT.
LUT, a lookup table, is basically the physical building block, the individual logic gate on that programmable chip.
Okay, so a 25% reduction in LUT usage literally means they eliminated a quarter of the physical hardware needed to run the AI just by teaching the AI to prefer cheaper math.
It is a massive breakthrough. But, we have to address the elephant in the room,
The damage.
the damage. All of these approximations, skipping math, swapping multipliers for adders, forcing the AI to use cheap weights, they inevitably introduce noise. The math is undeniably worse, and the AI's accuracy degrades. So, how do we fix it?
Well, looking at the architect's diagnostic matrix from our blueprint, there are two main strategies for recovering that lost accuracy. The first one is retraining.
Retraining is exactly what it sounds like. You essentially let the AI practice its task using the broken approximate math until it gets used to it and adjusts. It is highly effective, actually. You can recover up to 95% of the lost accuracy.
But the matrix shows a huge red warning bar for compute cost and emulation complexity.
Yeah.
Why is retraining so painful if it works so well?
Because to retrain it, you have to simulate the flawed approximate hardware inside a normal, perfect software environment. That requires immense computing power.
Oh, that makes sense.
Plus, if you are using a proprietary black box model, say you bought an AI from a vendor, but you don't own the original millions of images it was trained on, you literally can't retrain it. You don't have the data.
Which makes the second strategy on the matrix so fascinating, statistical error compensation. The blueprint says this requires zero retraining. Wait, clarify that for me. How do you fix an error if you don't know the exact right answer in the first place?
It sounds a bit like magic, but it uses something called control variates. Think of it like a slightly misaligned bathroom scale.
Okay, I'm listening.
If you know your scale always reads exactly 2 pounds lighter than reality because of some mechanical flaw, you don't need to completely rebuild the scale. You just step on it, see the number, and mathematically add 2 pounds in your head.
Oh, I see. Because the engineers designed the approximate hardware, they know exactly how it's flawed.
Precisely. They can calculate the statistical mean of the error, the average deviation that the approximate math will produce over millions of calculations. Then, they simply inject a constant correction term to nullify that average error on the fly.
So you're basically adding a tiny constant counterbalance to the end of the calculation to offset the missing math. And that takes zero retraining.
Zero retraining required.
So bringing this all together for you, the listener, if we look at the performance landscape graph in the blueprint, we see energy savings plotted against accuracy loss. And there is this highly clustered area right in the top left, the Pareto frontier sweet spot.
Right. And that sweet spot proves that perfection is actually the enemy of efficiency.
Because by pairing 8-bit precision scaling with these approximate shift and add circuits, and then using that statistical error compensation to patch the holes, architects are hitting a gold mine. They are seeing up to a 70% energy reduction for under 1.5% accuracy degradation on incredibly complex visual tasks.
It's an amazing trade-off.
You lose 1.5% accuracy, but your device's battery lasts nearly 3 times as long.
But that energy reduction unlocks capabilities that go far beyond just saving battery life. And this brings us to the hidden perks of approximation.
Yes. This is what we promised at the beginning of the deep dive. The hidden defensive perks. Let's start with the physical perk first, thermal cooling.
Remember earlier we talked about the danger of melting the battery?
Yeah, the Formula One car overheating.
Right. By drastically reducing the switching activity in the silicon, because we are skipping operations and using simple adders instead of heavy multipliers, we drastically lower the power density. This literally acts as a passive thermal management mechanism.
So it stops the heat before it even starts.
Exactly. It prevents hot spots from forming on the chip.
Yeah.
By making the math simpler, the chip physically runs cooler.
And then there's the digital perk, which is the part that genuinely took me by surprise. Defensive approximation, the cryptographic noise shield.
This is truly at the frontier of AI security right now. To understand it, you have to understand how hackers attack an AI. It's called an adversarial attack.
Okay, how did that work?
An attacker will take an image, say a stop sign, and they will inject microscopic, mathematically calculated static into the pixels.
So to a human eye, it still looks exactly like a normal stop sign.
Yes. But to an exact mathematically perfect AI, that specific static manipulates the billions of multiplications perfectly, tricking the AI into classifying the stop sign as a speed limit sign.
Which in a self-driving car is disastrous.
Absolutely disastrous.
But wait, an approximate chip isn't mathematically perfect.
Exactly. Because the approximate circuits have inherent mathematical noise built right into the silicon, that physical noise acts as a cryptographic shield.
Wow.
When the attacker's carefully calculated static enters the approximate chip, the chip's own physical imprecision scrambles the attacker's static. It completely swallows the attack.
So the fact that the computer is slightly confused actually protects it from being manipulated. It's like trying to hypnotize someone who isn't paying attention. The attack just bounces right off because the mind is wandering. The inherent noise of the hardware swallows the malicious noise of the hack. That is incredible.
It is a beautiful synergy. The very thing that makes the chip energy efficient also makes it inherently secure against algorithmic manipulation.
Okay, let's recap this journey for you really quickly. We started with a massive energy bottleneck, the fact that exact multiplication is starving edge AI of power and causing thermal throttling. We explored the atlas of approximation, finding intelligent ways to shrink data, skip math entirely, and pull answers from memory.
Right, and then we took a sledgehammer to the multiplier entirely, replacing it with bit shifts and cascading adder graphs.
We also explored how software has to meet hardware halfway. Using hardware-aware training, we can literally force the AI to learn its tasks using weights that are mathematically cheap to compute in silicon.
And finally, we saw how we can recover the lost accuracy using statistical control variates, adding that 2-pound mental adjustment to the scale, landing us in a sweet spot that yields a system that is cooler, vastly more energy efficient, and naturally resistant to hackers.
But as the architect's decision tree in our sources reminds us, there is no single silver bullet here, right?
No, definitely not. The future of edge AI depends on matching the specific technique to the specific dataset complexity and network size. Absolute precision is a luxury we can no longer afford on the edge. Hardware is no longer just a dumb, perfect vessel for code. It has to be an active, flawed, participating partner in the algorithm.
I love that. For decades, we've measured the progress of computing by its flawless, down-to-the-decimal precision. But if the most advanced artificial intelligence thrives on good enough math, on approximation, and on inherent noise, much like the human brain itself, what does that say about our own human obsession with perfection? Maybe true intelligence isn't about expending maximum energy to get the exact right answer every single time. Maybe it's about knowing exactly which corners are safe to cut. Thank you for joining us on this deep dive.